This video presentation is brought to you by the Pro Mathematics Academy.
Mic check 1 2. Mic check 1 2. Good morning, everyone. Welcome back to our course review sessions. And today we'll be looking at formal mathematics, of course, where I selected some past paper questions again, where we'll be going through the topics which we've covered before the closing of school, so that next week when we come back to school virtually, of course, we will be not so off in terms of understanding the concepts that will be coming. So I guess without further ado, I jump right in, and I think everything's set up. So as you can see, our first question here involves truth tables and the logical construction of an argument. All right. So I was told based on yesterday's session that I should allow you guys or give you guys the opportunity to attempt the questions before I jump right in. So I'm gonna be allotting 2 minutes before attempting any particular question, just so you guys can start and compare our solutions as I work through the questions. Okay, so throughout this time, you guys are encouraged to read the question and make a first attempt, at least part A, guys, because I think part A is fairly straightforward, right? And then you guys can compare your solution with what I propose. And also for the persons who are joining us for the first time, welcome. You're encouraged to use the chat room as much as possible, right? So that you can make queries inside the chat room, and then we can ask you to turn on your microphone if possible, or if it needs be, so you can voice your opinions more clearly. So please, guys, don't be shy. Yesterday's chat room took a long time before it got off the ground, but eventually, we saw where we were interacting inside the chat room. Guys, feel free to make any comments, ask questions, etc. Don't be shy, all right? Okay, guys, so by now we should have already put forward a possible answer for question number 1, part A, right? So as you can see, we're given the following argument. If silly things are fun, or children like movies, then Mr. Jones has a green lawn. If Mr. Jones has a green lawn, then children do not like movies. Therefore, either silly things are fun or Mr. Jones has a green lawn, right? And when we are given these type of questions, we want to take down each statement, right? Each proposition of the argument's construction. And we want to make note of them. So here I'll make a note of statement 1. And I'm going to write it, of course, in symbolic language, where S is silly things are fun, C, children like movies, and J, Mr. Jones has a green lawn. So the first statement says, silly things are fun, or children like movies implies Mr. Jones as a green lawn. And this is statement 1. Statement 2 implies that what? Mr. Jones as a green lawn implies children do not like movies. Statement 3 says to us that either silly things are fun or Mr. Jones as a green lawn. So that is S or J. So now that we have the 3 statements, we can write them as follows. So as we know the definition of an argument, definition of an argument is that we have proposition 1 and proposition 2, and however many propositions that we need, implying some final conclusion. So whenever we construct a mathematical argument or a logical argument, it should always be of this form. Okay? So here I gave you the 3 statements. It's now up to us to write down these 3 statements in the form of a mathematical argument, which means that we have first, S or C implies J as our first proposition, and J, I keep writing my J like that. J implies not C as our second proposition. And finally, the AND statement compounded there implies that C, the conclusion, S or J. So this would be our answer to part A. I know that this question might seem fairly simple, but it's best if we take our time just to write it down correctly. Now, part B says, use a truth table to determine whether this argument is valid. All right? We should use a truth table to determine whether this argument is a valid argument. And in doing so, I'll take this time to construct my truth table. In the meantime, I ask that you guys try to construct the truth table and work alongside me, okay? All right, so the first thing I put inside my truth table is S, C, and J. Of course, we're used to this type of construction. We've seen it many times, right? Let me rule out my table. So here we have truth, 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 false, 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 false. And you see we have an extra column right there. That's fine. This one is truth, truth, false, false, truth, truth, false, false. And then we have truth, false, truth, false, truth, false, truth, false. Now we need to look at our propositions and try to write them out inside of, or give them a row. So here, the first thing I'm going to construct is S or C. Now we know that our OR statement tends to be true. Well, let's say it tends to be false only when both statements are false. So we just need to look for S and C And here we recognize that it's false here and also false here, but it's true at every other value. We can now write down what? S or C implies J. Now we know that the implication statement is false only when the premise is true and the conclusion is false. Okay, guys? So this is very important for us to be able to evaluate an implied statement. So we say that the implied statement tends to be false only when the premise is true and the conclusion is false. So let's look at the premise here. Well, let's look at the conclusion. So the conclusion is J, and we want to look for those particular values of J when J is false and try to find out where in the premise we would have a truth value. So we see we have one here, we have one here, and we have one here. So because we are showing that S or C implies J, we need to look at J wherever J is false and then consider where in the premise would be true. And if we have those conditions being satisfied, then we realize that our implied statement would be false. So it's true everywhere else, but only false when the premise is true and the conclusion is false. Continuing, I can now write down my set of values for not C. Evaluating not C gives us false, false, true, true, false, false, true, true. So the next thing I want to write down after not C would be J implies not C. And as I said, to find out where in our truth table this type of construction would be false, we have to look for our conclusion wherever the conclusion is false. Right, so here our conclusion is not C, so we look at where in not C we have a false, and then we try to find out where in the premise we are still true. So we see that here we are still true, so that means this one is false. Here we are false, but inside of the premise we are false, so this is true. Here we are false, and inside the premise we are true, so that means the statement is false. Here we are false, and inside the premise we are false, so this is true. And then we can write down true for every other value. So guys, usually these type of constructions take a bit of work. What I can tell you is it's better to go slow and steady and get this question correct. All right. So, and remember, you're supposed to be working alongside me. If we have any concerns, we are encouraged to make them inside of the chat room. Okay. So my next line that I want to write down is S or C implies J and J implies not C. So let's see if we can construct that. So we have both of these propositions evaluated separately. Now we need to look at what the result is when we compound them. All right. So here we're looking at, see if I can put a highlight on what we're looking at here. We're looking at this particular set of values and these values. So we want to perform an AND statement between those two statements. So this then gives us false, false, true, false, 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 true, true. All right. And I hope that you guys are working alongside me, ensuring that I'm not making any mistakes here. So the next thing I want to write down is S or J. Now, S or J is pretty simple. We go back to our statements up here, right? And we perform a OR conjunction between both of those statements. So if either values are true, then we know it's going to be true and only false when both values are false. So let's look for when both values are false. So I see we have one here, and we also have one here. Otherwise, we say that we are true everywhere else. Nice. So now we can construct the final statement of our logical argument, which should be S or C implies J, and J implies not C implies S or J. So here we see that our conclusion is S or J, which means that we should look inside of S or J where we are false, and then look in the premise where we are true. So here we see that we have false and false, so that is true. We see that here we have false and true, so that is not true. That is false. So therefore we are true everywhere else. And so our final conclusion is that the argument presented is not a valid argument. All right. And how do we know that it's not a valid argument? Because we do not have the argument being a tautology. All right, guys. Remember, if the construction of the argument turns out to be a tautology, then we say that the argument is a valid argument. And this question asks us to determine whether or not it's a valid argument. So here we have shown that it is not. Are you with me? So one major aspect of this course is the fact that we need to know how to evaluate logical statements, logical arguments, and construct truth tables to prove that. All right, so without further ado, guys, I hope that you guys are attempting the question on your side. In order to get the best result out of these sessions, it is important for you to participate, at least as an individual. All right. So moving right along into question number 2. Moving right along into question number 2. And this one is fairly simple, guys, but it's important that we remember these concepts. All right, so for question number 2, we realize that we have a question that deals with relations. An important part of formal mathematics is the concept of relations, where we talk about the equivalence relation and also what is referred to as a equivalence class. All right. So here you guys have 2 minutes to read this question as well as to give your first attempt, or at least to get a head start ahead of me so you can see where possible you might have gone wrong. All right, so I read it for you. Let rho be the relation on Z such that M rho n, well, we can say that M relates to n if and only if M minus n is a multiple of 7. Show that the relation rho is an equivalence relation. Part B says find the equivalence class of 7 denoted by that symbol right there. So go ahead, guys. How do we prove that something is an equivalence relation? We have to prove 3 things. What are those 3 things? That's right. And if you prove those three things, then it is an equivalence relation. So for this particular question, we just have to demonstrate that this relation satisfies those three conditions, and then we are finished. So go ahead, guys. 60 seconds remaining. 60 seconds remaining. Guys, and please don't be afraid to say something inside of the chat, all right? It's looking a bit lonely over here. It's looking a bit lonely inside the chat room, guys. Let us know you are here by posting something inside the chat room. Let us know you're here by posting something inside of the chat room. Nice. And we see we have a comment right there. That's what I like to see, guys. I like to see interaction happening inside the chat room. I want to know that I'm not here by myself. Awesome, awesome, awesome from Swan. Guys, I can't take the funny names, okay? Please try to be please try to be fair in your naming of yourselves, okay? Put names that oh, it's your real name? Wow. Okay, Swan, I see you. Nice, nice. That's what I like to see over there in the chat room. So guys, don't be afraid to post inside the chat room, okay? Awesome, awesome, nice. So let's jump right into this question. Whoa. Had some feedback there. Sorry about that, guys. So to show that something is an equivalence relation, right? We need to show that it satisfies three conditions. So let's say the relation R must satisfy three things. One, R must be reflexive, right? Is that true? What does it mean to be reflexive? That means X relates to X for all X. Two, R must be, see I missed B right there. R must be what? Symmetric. So what does it mean to be symmetric? That means X relates to Y, implies that Y relates to X. Number three, R must be what we call transitive. So to be transitive, we say that X relates to Y and Y relates to X, implies that, no, Y relates to Z, thank you for that correction, right? Implies that X relates to Z, nice. So let's go. So for our relation rho, right, and this is just the background idea that we are covering here, okay, guys? Just to remind you what the conditions are before jumping into the actual working out of the question. So for M rho n, right, we have what? M, and this is for reflexive, which is for the first condition. So M relates to M, right? If and only if M minus M is a multiple of 7. So this implies that M minus M is equal to 0, which is equal to 0 multiplied by 7. So if it's 0 multiplied by 7, then we can say that or relation rho is reflexive. So 2, let's say x, I'm tempted to put the relation as R. Let's say x relates to y, implies that x minus y is equal to 7 times k, right? Where k is an element of integers. This implies that what? Y minus x is equal to negative 7k, right? Which implies that y minus x is equal to 7 times negative k. And we see that negative k is an element of, let's say, and negative k is an element of z. So this means that y relates to x. So we have just proven that. Oh my God, I just put the R symbol. Rho, nice. I know it looks like a P, but that's our version of rho. So this means that rho is symmetric. Nice. So now we're to prove that. Now we're to prove that what? Rho is transitive. So we have x rho y and y rho z implies that x minus y is a multiple of what? 7, and y minus z is also a multiple of 7. Here I can say k and q are elements of z. So this is 7q, right? So this implies that, what can I do to get both statements to relate to each other? Add, nice. And I see we have some action there in the chat room. That's what I like to see. So here, if we add both of these equations, we see that x minus y plus y minus z is equal to 7k plus 7q. Let's write that a little bit better. 7q. So this means that x take away z is equal to 7 times k plus q, and k plus q is an member of z. So this implies that x relates to, keep doing that, x relates to z. So therefore, the relation rho is transitive. Thus, the relation rho is an equivalence relation. All right. So in order to prove that something is an equivalence relation, we have to show that we have satisfied these 3 conditions. All right. And more or less, the questions are of this type of difficulty. It's not that it's difficult, but if you don't know what you're doing, you cannot prove the results. All right. So now it says find the equivalence class of, oh wow, guys, I just checked my my timer and I realized that we have less than a minute to go. So I'm going to ask you guys to log back in exactly 30 seconds after the meeting has ended. All right. So in exactly 30 seconds. All right. See you guys soon. Okay, guys, so we're back. I apologize for any inconvenience caused in the interim. So, as you can see, we're about to close off on this particular question. So let's find the equivalence class of 7, right? And the notation for equivalence class is this square bracket around whatever the element is. So once you see a square bracket around x, then you read that as the equivalence class of x. So here they're asking us to find the equivalence class of 7. So what is the equivalence class by definition? So the equivalence class, let's look at the definition. Right, in words, the equivalence class represents all the numbers that are related to each other. So this is a set of numbers, let's say numbers in this particular example, but it's a set of elements that are related to each other. So let's go. So the equivalence class of 7 in this particular example is equal to the set of all x's, right? Such that x is related to 7. So we can write that out as set of all x's such that x minus 7, right, is a multiple of It's a multiple of 7. This means that we have the set of x such that x minus 7 is equal to 7 times k. Oh, I'm using r. My bad, guys. I tend to do that sometimes. I apologize. So, you guys know what I'm saying. Whatever the relation is, all right, guys? So, here, we see that x minus 7 is a multiple of 7. So, can I simplify that any further? Let's try. So, x is equal to 7 times k plus 1. So that is the set of all numbers that are multiples of 7. So the equivalence class of 7 is the set of multiples of 7. All right, so once you're given, they use R all the time in the lectures. That's right. So I guess that's why I'm programmed to use R. Well, that's fine, guys. Whatever the relation is, if you interchange a symbol with R, I'm sure you won't be penalized too much for that. All right, so don't worry about interchanging the symbol that they give you with R. All right, so what I was saying about the equivalence class is that whenever you're given a question on an equivalence relation, bear in mind that they can always ask you to find the equivalence class of that equivalence relation, all right? So that is very, very important. Nice. And so at this time we go into another question. Here, we're still on this past paper, guys. In case you guys are wondering what past paper is this that I'm working, I believe it's a 2017 exam. All right, just so that everybody can feel more comfortable knowing that I'm not taking these questions out of the air. All right. So the next question we look at, guys, and remember this review session is basically geared at covering or reviewing what we've already done so far, you know, bringing us up to speed with everything that we've learned thus far. All right, so it's really a refresher. So you might see some questions that you have done before, but nothing beats practicing and doing these questions again. All right, guys. So I'm sure some of us have seen this question before, but nonetheless, we're going to execute it one more time. So this question is on the topic of binary operations, and as we know, binary operations it's a very important topic when it comes on to formal mathematics. It's always tested on the final exam, so you guys need to absolutely be on your toes when it comes on to. So somebody's asking to go back 1 sec. Sure. And guys, please remember that these sessions are being recorded. All right. Please keep in mind that these sessions are being recorded. So at a future date, we'll have these videos posted on the Pro Math Academy YouTube channel. So guys, please remember to like, share, subscribe. You go over that side. I'll post a link in the chat room soon. So you guys can just hit that. Go over to the Pro Math Academy YouTube channel and hit subscribe, notification bell for future post notification. All right. So nice. So let's go back into the question. All right. So don't worry about if you missed something, guys. The video will be posted. All right. So here we're given a particular binary relation star, which is on the set R cross R, right? Which says that, and sometimes it's good to just write down these things. AB star CD is equal to AC, right? Comma B plus D. So what you realize that they're doing here is this element and this element goes here as a product, and this element goes here as a sum, right? And it's important to make these observations known, because that's the strategy that we will be using to answer all these questions regarding associativity and commutativity. All right, guys, you'll see what I mean in just a second. So let's go. So how do we prove that something is associative? How do we prove that something is associative? Right, we have to show that what? A, B, star, CD, star, X, Y is equivalent to AB, star, CD, star, XY. And here, we took the common courtesy to perform the operation on the first two elements. And then over on our right-hand side, we perform the operation on the second two elements. So in particular about this proof, what I would say is that sometimes when we're proving things, we want to start with the left-hand side and work all the way to the right-hand side, or starting from the right-hand side and work all the way to the left-hand side. But for this particular example, we're gonna work both sides until they are equal. We're gonna work the left-hand side downwards, and then we're gonna work the right-hand side downwards and see if the results are the same. If they are, then we have proven that which we were supposed to prove. All right, so left-hand side. So we already know that the first two elements, when the binary operation is performed, we end up with AC B plus D, and now we are gonna star that with X, Y. So as I said, whenever we're doing the star operation, we take the first two elements, we take the first element from both tuples and multiply them. So that means the result here is gonna be ACX, and then the second element inside the tuple represents the sum of the second two elements from whatever we were using. So this is B plus D plus Y. Nice. And I think I'll stop there, and then going over to our right-hand side, right, we have the operation being performed on the second two elements. So this is going to be A plus AB star CX, comma, D plus Y. And if I extend this further one more time, I end up with ACX, comma, B plus D plus Y. And if I look at these two expressions, I realize that the left-hand side is equal to the right-hand side. So therefore, quite easily done. All right. So I hope that we do not have any questions regarding that particular result. All right. And I realize that I didn't give you guys a chance to actually work that question. My apologies. All right. We'll get a chance to show that it is commutative. So is the operation commutative? And let me just write the operation one more time so we can see that. So AB star CD is equal to AC, comma, B plus D. Is this operation commutative? So what is the definition of commutativity? What is the definition? Guys, we've been learning these things since we're in high school. Commutative. What does it mean to be commutative? So let's remind ourselves of the definition. So you say if an operation is commutative, then let's say the operation in this case is box. A box B is equal to B box A. So if an operation box is commutative, then A box B is equal to B box A. So now, for our question, we have star as our operation. So we need to show that. We need to show that what? AB star CD is equal to CD star AB. So go ahead, guys. Take 2 minutes. Take 2 minutes to box up that question. Take 2 minutes to do that question, guys. Okay, guys, so I just posted the link to the Pro Math Academy YouTube channel. Guys, remember, if you want to receive the future post notification on when this video will be uploaded, you have to hit the subscribe button as well as the notification bell. All right, so let's jump right back into our question, right? And you guys should have already made a full attempt to show that this question is indeed commutative, right? So here, we already know that AB star CD is equal to A C B plus D, which is the same as C A D plus B, right? Which is actually C D star AB. All right, guys, so that one is not so straightforward, but if we look into it, we realize that. Remember, I said the operation star works in this way, where we take the first element from the first one and the first element from the second one, we multiply them, right? And we take the second element from the first tuple and the second element from the second tuple, and we add them. All right, so that's what is going on here in this transition. So now we need to show that the operation is, as an identity element. All right, so let me see if I can reinsert this picture. So determine whether a star has an identity element. Anybody remembers the definition of an identity element? What does it mean to be an identity? Go ahead. Anyone in the chat room? Not seeing any action inside the chat room. So Jasford is saying that it's the thingy with E. I guess you're somewhat correct. Anybody else with any other comments? I see we have a brains box inside of the chat room. All right, big up yourself, brains box. All right, so we see that we have the definition of the identity was just given to us. So we say that an identity element E is such that X star E is equal to X and E star X is equal to X. So how do we apply this to our question? We have to say that E1, right? E1, comma, E2, let's call her E1, E2, or identity element, star XY is equal to XY. And if we solve that equation, we should be able to come up with the values of E1 and E2. All right, guys? If we solve this equation, we should be able to come up with the values of E1 and E2. So let's go. So this means E1, comma, E2 star XY is equal to E1 times X, comma, E2 plus Y. And we know that E1X, comma, E2 plus Y should be the same as X, Y. So this then means that what? E1 times X is equal to X, and E2 plus Y is equal to Y. Solving these equations simultaneously gives us X equal, sorry, I can't actually solve this for X. We have to solve it for E. E is equal to what? Somebody said E is equal to 1. Right? And E2 is equal to 0. So we recognize that E1 is equal to 1 and E2 is equal to 2. This means our identity element is given by 1, 0. Right? Nice. Nice. And I love to see the interaction inside of the chat room, but I guess some persons are okay watching from the sidelines. I mean, nothing is wrong with that, but I like when persons interact with me inside of the chat room. All right. And sometimes even turn on your mic, but not without my permission. All right. Now, the next part of the question asks us to do what? Next part of the question asks us to determine, right, which elements, if any, have inverses. So let's go. Let's go. Brain box. Brain box, where are you at? What's the definition of an inverse element? What's the definition of an inverse element? Let's go. Come on, guys. I'm not seeing any interaction inside the chat room. What's the definition of an inverse element? It seems Brainbox has come to our rescue and we have Swan there confirming, right? So let X star, Y star be the inverse of XY. Let X star, Y star be the inverse of X, Y. Then we see that X star, well, I guess I shouldn't have said star in this particular example because the operation is star. So it's kind of funny, sounds funny. Let's just call the operation. So this means X star, Y star operation, XY is equal to the identity element. So in order for us to define the inverse, we need to use the identity element. Yes, and somebody said we can put a bar over X and Y. Awesome, Mr. Michael. Big up yourself, all right? So this means that when I perform my operation here, I get X star times X, comma, Y star plus Y is equal to 1, 0. So this means that X star times X is equal to 1 and Y star plus Y is equal to 0. So this means that X star is equal to 1 divided by X and Y star is equal to the negative of Y. Now I believe this question said determine which, if any, elements of inverses underneath this operation, right? So here we see that all XY have inverses except which ones? Where X equal 0. All right, nice. And we see the party is getting started inside of the chat room. Awesome, guys. Everyone inside of the chat room, let's pick up yourselves, all right? So let's go. The next part of the question, well, I believe we're finished with this question, actually. I believe we're finished with this question. So far, let's just summarize what we've been doing so far. So far, we've been looking at topics related to logic and the construction of a mathematical argument, the truth table form, as well as we looked at the equivalence relation and how to find the equivalence class given a particular equivalence relation. Also, we've completed the concept of a binary operation in terms of showing that the operation is commutative, associative, as well as finding the inverse elements and identity elements underneath the particular binary operation. And these topics so far represent the core of what we will learn inside of formal mathematics going forward in higher level mathematics, or even if you're a person majoring in chemistry, you know, you'll see where some of this really laid a foundation in the critical aspects of what you'll be applying in your future work. All right. So the next topic that I will look at, right, is something that I believe persons have, I guess I have two more topics, but both can be combined into one topic, right? Both can be combined into one topic. And based on the time constraint of today, guys, remember this session is supposed to be 1.5 hours. All right, guys, it's not that we're here to cover the entire syllabus. We're just here to refresh our minds, you know, so that next week when we come back to school, we'll be ready. All right, so please, if I don't touch on something, guys, it's not possible to touch on every single thing. It's only a one session, all right? So just come out to the future sessions, all right, guys? Well, I mean, when school starts back, I'll be having my regular tutorials, but it will still be online, and you guys are welcome to join, all right? Also, guys, remember to go over to ProMath Academy and what? Okay, Mr. Michael, I see you. Right? Remember to go over to ProMath Academy, guys, and hit the notification bell for future post notifications. All right, I'll be putting out some videos related to, you know, coursework, calculus, and formal maths. All right. So I can guarantee you, I'm not just trying to boost you up here. I'm actually gonna be posting stuff. All right. And for persons who were here in yesterday's session, guys, today we will actually post. We'll actually post a video from yesterday. All right. So I'm premiering that video tonight at 8:30. Okay. I believe the link will be out before that for some persons to verify or confirm, give their supervisory comments. But for the main population, we'll be premiering it at 8 o'clock. So, and that's for persons who are doing calculus. All right. So if you're not doing calculus, it's fine. You don't have to come over and watch the premiere video with us. But everyone else, you're welcome to join me, you know, get some popcorn or whatever and watch the premiere. All right. So the topics that I'll be going into now will be proofs. In particular, I want to spend some time on proof by mathematical induction because I realize that, you know, it's oftentimes difficult because if you don't get the induction in a particular way, then it proves to be more difficult than it actually is. All right. So I'm going to be looking at mathematical induction as well as, a direct proof. All right. And then we'll be out of here. So I see that I have 8 minutes remaining on the clock. So it means that this session will have to be extended by one more session, but I can guarantee that the next session will not be extended for the full 40 minutes. Okay, guys, I'll go for maybe 15. So without further ado, let me drop in our questions so we can look at that. I guess I should have done that while I was here talking. All right, so the first question, guys, we see that the first question is a direct proof, right, which asks us to show that, right, and this is a basic one, but it's just to get our minds back in the right frame, okay, guys? Because I know persons, when they see this, they tend to freeze up, all right? So the first proof says, prove that if m is an odd integer, then m squared takes the form 4k plus 1 for some k inside of the set of integers. All right. So this is what we call a direct proof. And as you know, there are 3 types of proofs, but I can't go into all of them today, guys. So I'm going to just be looking at a direct proof for this particular case. But in future, we'll be looking at other types of proofs. All right. So this is a direct proof, meaning we start with the premise. It says if m is an odd integer, right? And then we work towards showing that the conclusion has to follow. All right. So now, if m is odd, right? This implies that m is equal to 2, I don't want to say k here, guys. I'm going to say 2p plus 1, where p is an element of z. All right. So this means that now we have to try and look at the conclusion. It says m squared is equal to that. So now we look at m squared. M squared is equal to 2 times p plus 1 all squared. This means that m squared is equal to, when I expand this. I know some of us have problems expanding things. So I'm gonna just write it out in this form. So this means m squared is equal to 4p squared plus 2p plus 2p plus 1. This means that we have m squared equals 4p squared plus 4p plus 1. This means that I can now say m squared is equal to 4 times p squared plus p plus 1. And if we look at this, guys, if we look at this, yes. So somebody is asking if this is a direct proof. Yes, it is indeed a direct proof, all right? So what we find here is that we can say p squared plus p is an element of what? Z. Are you guys seeing that? P squared plus p is an element of Z. So therefore we can say m squared is equal to 4 times k plus 1, and then we put our quite easily done right there. So as I say, this is an example of a direct proof, and we need to be comfortable with these type of proofs, okay, guys? Because I find that a lot of persons, when they get these proofs, they tend to overthink it. They tend to try and do contrapositive, some proving all different type of nonsense, contradiction, and blah, blah, blah. Guys, listen, if you get this question, straightforward. We just want to prove that if the premise is true, the conclusion follows. Don't overthink it, all right? So somebody is saying where k is an element of Z. I'm just going to say k is equal to p squared plus p. All right. So if that is not to your liking, then you can put k is an element of Z. As I say, guys, you are encouraged to voice your concerns inside of the chat room, guys. I love it, to be honest. I hate being over here all by myself. So guys, put your comments. If you see me do something that you think you would do it another way, go ahead, guys. We welcome all your feedback, all right? So that part covers the direct proof, and then now I'll go into the whole mathematical induction. Since I have 3 minutes, I'm just gonna spend some time talking about the process of mathematical induction. And then once the meeting ends, then we jump right back in and we look at the question, or I'm not sure what you guys prefer. But for my first mathematical induction question, since it's so difficult, or maybe not, but because you guys will think that it's difficult, I'm gonna put the question here on the screen so you can think about it in the meantime. You guys have never seen an induction question like this before in your life. So I want you guys to take some time and think about what approach you could use to work this question, all right? So let's bring this up. So I know some persons are excited because they think they've seen it all, but I'm telling you, you've never seen a mathematical induction question like this before in your life. All right. So here we go. Let's crop this down some more and let me read this one for you. Because based on the time constraint, guys, I think we'll just spend some time talking about this, or maybe, I'm not sure. Let's see how it goes. So still cropping this down. Okay. And I think that's good enough. Okay. So as you guys can see, right, after assuming that the first derivative of t with respect to t is 1, prove by mathematical induction that the derivative of x raised to the m is equal to m times x raised to the m minus 1 for all m inside of the set of natural numbers. Wow. Guys, have you ever seen a mathematical induction question like this? I guess we have less than a minute, guys, so I'm going to just close out this session. And hold on, guys. When I open a new chat, we can start our discussion. We can start our discussion over that side, okay? So in exactly 30 seconds, I'm going to encourage you guys to log back in. All right. So welcome again, brilliant students of the University of the West Indies. Right? We are on the last question of today's session. Guys, it was my intention to work out more questions, but based on the time and everything, guys, I don't want to be here too long doing these things. I know some of us are enjoying the session, but guys, when school start back, just come over to my tutorial, all right? And I'm sure the vibe will continue just the same. So with that said, guys, remember inside the chat room right now, I just posted the Pro Math Academy YouTube channel's link. Remember to go over there. The video from this session will be posted there. So if you came in late and you feel like you missed out on a lot of the session, guys, just go over to the Pro Math Academy YouTube channel, hit the notification bell. And in the future, when the video is premiered or posted, you will be notified and you can watch the video and pause it and rewind and listen to my voice over and over and over again, explaining these same topics. All right. So with that said, I jump back into the question. What happened to my beautiful people who were there? Yes, awesome. We were saying that we've never seen an M induction question like this before in our lives. Nice. But notice it's just a 4 marks question. And I'm saying this question, I mean, it's not too difficult, but if you don't know what to do, then it can seem like. So we see that Ramoy is stepping up to the plate. We'll seek to express that. The concept is still the same. Jason Chambers says that, okay, assume M equal 1. I guess, yes, that is true. That is true. And I love the way that we're interacting right now inside of the chat room, guys. Wonderful. Wonderful. But I still would love to hear from some of the other brilliant students of the University of the West Indies, Mona. All right. I know that you guys are out there just watching from the sideline, you know, probably smirking. But yeah. So guys, go ahead and see if you can get in a quick attempt, guys. See if you can get in a quick attempt and tell me where you think that you cannot go any further. Where you think that you cannot go any further. All right, guys? Where you think you cannot go any further. Let's get in an attempt, guys, right now. Let's try to prove that the statement is true for n equal 1 or for m equal 1, rather. So, Pookie, big up yourself. I see that you were here yesterday and you're back again today. Awesome sauce. So, guys, go ahead. Mr. Jasford said that it is true for n equal 1. Okay. Awesome. Do we have any other comments? Do we have any other comments, guys? Go ahead. Guys, don't be shy. So, I guess since everybody is waiting, let me check inside the chat room to make sure everybody is here. Awesome. Awesome. And you see we're back up to 39 persons again, just like yesterday. Awesome, guys. It's good to see that, you know, the numbers are turning out. All right. No. I would never do something like that. All right. So let's jump right in. So as somebody said, the principle of mathematical induction, right? Let's look into it. So somebody said the first step is to show that the statement is true for m equals 1. 2, assume that the statement is true for m equals k. Then number 3, we use the assumption to show that P of K, right? P of K, which is the statement evaluated at K, implies P of K plus 1. All right? And remember earlier where we mentioned that the proof that we did was a direct proof. Oftentimes, we want to do a direct proof when we get to this step. All right? When we get to step 3, we want to do a direct proof. So I know that some persons oftentimes get to this step and they are confounded, right? But what you need to keep in mind is that what you're doing is a direct proof. All right, you just need to know how you can incorporate your statements to show that P of K implies P of K plus 1. All right, and part 4 of our M induction process, we have to conclude that the statement Pn is true for all n. So guys, please keep your eyes locked to the screen right now. All right, for this particular M induction, you've never seen something like this before. I'm sure you're about to learn something. All right. I'm sure a lot of us are out there wondering, how the hell am I going to prove this right now? So keep your eyes glued to the screen. Don't blink and look at this. All right. So in our comment section, I saw that persons were saying they found that it was true for m equal 1. I found that to be interesting. And let me tell you why. Because it said in the question, the first derivative of t with respect to t is 1. Wow. The question told us, all right? The question told us that the first derivative of t with respect to t is 1. So really and truly, it wasn't a working out, guys. It wasn't a working out. But if you worked out something, that's wonderful. But it was No, you have nothing to be ashamed about. You have nothing to be ashamed about. All right, guys? I'm just saying that if we were reading the question, because it said, after assuming that the first derivative of t with respect to t is equal to 1, prove by mathematical induction. All right? No, I'm not dealing with you anyway at all, guys. To be honest, I'm just saying that when we don't read the question, we tend to put ourselves in situations. All right? So please, guys, read the questions and try to understand what the question is saying, because sometimes the question gives you information that you don't have to. Yes, exactly. You're giving yourselves extra work. All right, guys? So please, Pookie, I apologize if I made you feel any way. You know that I really appreciate you. In particular, you've been here through thick and thin. So no, I'm not dealing with you guys any way at all. All right? So for m equal 1, we can say that it was given as true. All right. For m equal 1, it was given as true from the instruction, or from, yeah, I can say from the instruction. All right, guys. Hello. Nice. So now, so this is step 1. Now we're at step 2. Assume that the statement is true for m equals k. That is the derivative with respect to x of x to the k is equal to k times x raised to the k minus 1. Are you guys with me? So we are assuming that this is true. And then for step 3, right, if you look back at what I said, we have to use the fact that P of K is true implies that P of K plus 1 is also true. All right. So we're performing this proof. We're doing a direct proof, right, which takes into consideration P of K, and we're required to show that that implication follows. So now, P of K plus 1, right, is the derivative with respect to x of x to the k plus 1, right? So if we look at this, we can say that this implies that the derivative with respect to x of x to the k plus 1 is the same as the derivative with respect to x of x times x to the k. Because you see, when you have your induction question, guys, it's very important to always try to see how we can use what we have in our assumption, right? And that is the key thing, right? So taking your P of K plus 1 statement, it's very important to see how you can incorporate the P of K statement inside of our P of K plus 1, all right? Nice. So here, somebody already realized where I'm going with this. I know some persons realize where I'm going with this. I'm about to perform the product rule. All right, guys, I'm about to perform the product rule of differentiation. Are you with me? Somebody said, how product rule drop in? Product rule have to drop in, guys, because here we have x to the k, and we have x to the k plus 1, and we want to rewrite it in terms of something involving x to the k. All right? And that's the trick in all induction questions. You have to always try to get your P of K statement to come out inside of whatever direct proof you will be doing. All right, so we know that the product rule of differentiation says that what? Derivative of our product is equal to the first times the derivative of the second plus the second times the derivative of the first. Wow. Wow, you notice that I didn't rush to write in the derivative of x with respect to x is equal to 1 right here. I didn't rush to write that in, guys, because what I want you to realize is that it is given in the question, and we're just incorporating these facts. All right, just incorporating these facts into our working out. All right. Yeah, man. Induction with differentiation. Big up yourself, Kayla. First time having you comment in the chat room. I see that the question really must have been something that was, speaking to you for you to jump out and give us your feedback. But as I said, guys, I welcome all the feedback right now, guys. Just jump in and let us know what are your thoughts. All right. So this then gives us what? X times, and we're going to incorporate our implied statement right here. What is the derivative of x to the k? We said that the derivative of x to the k is, we said that it is what? K times x raised to the k minus 1. So that's exactly what I'm going to put in right here, right? Coming from our implied or assumption. So then I'm adding x to the k multiplied by 1. So this means we now end up with k times x to the k minus 1 plus x to the k, which is equal to k times x to the k plus x to the k, which implies that we now have k plus 1 times x to the k. And if you look at that, we wanted to show that the derivative with respect to x of x to the k plus 1 is equal to k plus 1 times x to the k. So we wanted to show that, and we have shown it. So someone is saying that they are lost. Let's look back from everything in the red ink. Okay, so I guess I can see that section. So I needed to confirm if this is the section you're talking about. Mr. Jasford. Awesome. So what I did there is I performed the product rule of differentiation. All right. Are you with me? I perform the product rule of differentiation. You remember the product rule? Yes, the product rule says that if you are differentiating the product of two functions, let's put it in this section, the derivative of u times v is equal to u v prime plus v u prime. Correct? Nice. So if you look at my function, if you look at my function here, we have the derivative of a product, right? We have the derivative of a product right here. Right? X times x to the k. So that is the trick. Nice, nice, nice. So once we recognize that we have to perform the product rule of differentiation, then everything else is much of a process of simplification or simplifying the expression. All right. So now that we have proven that P of K implies P of K plus 1, my conclusion, I'm sure everyone knows what the conclusion is. We conclude that the statement derivative with respect to x of x to the m is equal to m x to the m minus 1 is true for all m by the principle of mathematical induction. All right, guys. So, guys, go ahead. Let me know what are your thoughts on this question in particular in the comment section right now. Do you think that the question was difficult? Do you think that the question was easy? What is it that could have made this question easier to interpret so that you knew that this is the process that you could have taken? Any type of comments regarding this question, guys? Do you think that if you see a similar question about integration, you could have performed, you could have proven that it is also true for the integral? Stuff like that, guys. So, as I say, I have some more mathematical induction questions, but because of the time constraint for today's session, guys, I am going to be closing off here. Guys, please, if you have any questions regarding any of the any questions that we did today, please let me know. And guys, we'll be sending out some surveys / review forms for you guys to fill out after the session to let us know where we could have improved or where in particular in the session you enjoyed. Guys, please fill out those surveys. Please, 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 please. Also, as I said, I cannot say this enough. Go over to the ProMath Academy YouTube channel and hit the notification bell. All right. Yes, man. I see that we have some 10 out of 10s right there. Guys, make sure you put that inside of the surveys. I saw that Daniel just. Daniel, you want to grace them with your last few words right now?
Yes, sure. Okay,
go ahead.
Thank you guys for coming out to the session. It seems like it was really, really useful. I personally don't do math, but I'm just here making sure that everything is running smoothly. So thank you guys for coming out. Again, there's computing tomorrow, as well as chemistry tomorrow, and then physics is on Saturday. Town hall is tomorrow morning. So please stay in the loop and please fill out the feedback form so I can know how to change or improve the sessions going forward. But thank you again, guys. Later.
Daniel, I see that Mr. Jasford has a question for you there.
Let me just check. Oh, am I running? Yes, I am running for, I can say that, yeah. I'm running for SciTech, but these sessions are more for the benefit of students because I saw where I personally could have used a refresher for some of my computing courses. Then we said, why not do it for like all the courses? Just ask the tutors if they'd be willing to do it. So yeah, yes, I am running for something just good. Any more questions, feel free to throw them at me. If that's all, then we can end here. Thank you guys again. No, I'm not for guild president. I've gotten that way too many times. No, I'm not running for guild president, just for SciTech guild president, yeah, or SciTech rep on the guild. Thank you, Donja. I appreciate it. Computing is 1161 tomorrow. I'm trying to get for 1210, but the tutor says that he can't connect to Zoom or something of the sort. So what I might do is I actually hosted a tutorial, like an exam review session last semester. So I might actually just post some of the videos from that for people. The time for 1161 is 12 p.m. and then chemistry is 0902, which is prelim B, and that's at 1 p.m. Again, all of the sessions are like 1.5 hours to 2 hours. Yeah, man, big up everybody. Yeah, Pookie. All right. Respect. Good day, everybody.
All right, guys. So I see that we have reached the end. Yeah, man, Danja, big up yourself. We have reached the end of our review session. Honestly, you know, I guess saying goodbye is always a hard thing for me. But this is not goodbye, guys. This is until next time, because next week school reopens, and I'm sure that we would really appreciate, you know, we would really appreciate having tutorials of this form. So guys, again, remember, I cannot say this enough, guys. The link for the YouTube channel, I'm gonna send it right now in the chat room, all right? Just so you guys can see it again. All right, so we have and guys, remember to fill out the forms. Remember to fill out the forms. Remember to go over to the YouTube channel, because this video will be posted, all right? So, and remember, we'll be posting videos in the future, all right? So it's a win-win situation for both of us. So guys, I officially call this session to an end. All right, it was really my pleasure inculcating you guys today as it relates to the art and science of the mathematics of formal mathematics. All right, so everybody, thanks again. You know, it wouldn't have been possible without you. All right, so see all of you guys next week. God bless and stay safe, okay, guys? I know in this time, Corona is attacking everybody, but we have to try our best to just be as safe as possible. All right. Peace out. Daniel here from the Pro Mathematics Academy. Wishing you guys all the best.
That is it for this video. Please remember to hit the notification bell, like, share, and subscribe for future post notification.